let me see. So we have a homework to do before we start something new. Our homework was on, I can't even remember what it was. I know it's fields. Was it magnetic field? I don't remember. What was the last one? Was it magnetic fields? What's it magnetic fields? That was the homework. Are you sure? Did we do the homework for this?
Yeah.
Oh, we did. Then we go on to the next lesson, is it?
Yeah.
Are you sure we did the homework? I don't remember doing it.
Yeah.
Let me double check.
That makes sense. No, first lesson. You did homework and after that you did past paper. Yeah.
Ah, yeah. I do remember doing this one at the end where it's travelling in a circle. Yeah. So then we're on to the next lesson. Okay. We'll turn the light off. Electromagnetism. Sorry, do you have the title? You wrote this down already, the title? Yeah, okay. Electromagnetism. Okay, so a couple of equations we'll be looking at. Right. Last time, previously in physics class, we saw that a charge moving in a magnetic field would experience a force. And we got this by using the left-hand rule. So here, let's see, from north to south, so the field is going that way, the current is going to the right, so the force is going up. So this particle, if it was a positive particle, will curve up. Thumb is pointing up. Now, current I is just a charge per unit time. Do you remember the formula with Q in it? Q equals IT. Do you remember that from electricity? Do you remember we had this yes, Q equals IT. This formula from electricity. That the charge is the current multiplied by the time, or if you want that the current is the charge divided by the time. Do you remember these from electricity? So, when we have a current moving, we can use the left-hand rule as well, because a current is just a charge moving. So let's see what formula we can make. So we imagine we have our current, and let's say this wire is length L. And let's say we have our magnetic field. So, you know, we'll put the north here and the south here, and the magnetic field is going this way, and that's it, B. So in this diagram you see the field is going up and the current is going to the right, so the force is coming to you and the current is going this way. Question? Yeah? No. So let's calculate the force here. So remember last time we had the formula that the force, actually let me draw it in here. So we picture all the charges moving along here. So the force equals Q V B. But what's V? Well, that's the velocity of the charge. That's how quickly these charges are moving. What's another formula for velocity? Distance. Remember the triangle? Distance, speed, time. So another formula for speed, distance over time. So that's L over T. But you also have to remember that Q equals I T. So then this becomes I T L B over T. And they cancel. So you get B I L. So when you have a current in a magnetic field, this wire will feel a force. Will feel the force going out of the page. And the formula is B I L. So this is our first formula here.
Why do you use flow?
The length of the wire. Yeah? We're good? Okay, so let's go back here. So we have F equals BIL, we just said. In this formula, the current is perpendicular to the field. So it's important to remember that these two, the field and the current, are at 90 degrees. If it was not perpendicular, that is, if it was at an angle theta, but then let's see what the formula is. So not really too much of a surprise. If it was at a different angle, like for example, if I draw the current here at a bit of an angle, or maybe actually, you know what, let me just draw that again, but instead of moving the field, I'll move the wire. So the wire, instead of being horizontal, let's imagine the wire is going like this. And this angle here, instead of being 90, is theta. Okay, so if you were to resolve this into two directions, one going this way and one going this way, will this be cos or sine? Try again. It's cos because it's touching theta. This one here is sine. So you actually only care about the sine part, because you only care when the current and the field are perpendicular. If they were parallel, if the current and the field are in the same direction, nothing happens. They have to be perpendicular. And the reason they have to be perpendicular is for this formula with your hand. You see, in this formula with your hand, all the angles are 90. So basically the only difference is if it's not 90, if it's theta instead of 90, then the formula just simply gets a sine theta. So please make note of that, yes?
Sine theta instead of, or the formula just add the sine theta.
Just add the sine theta. In fact, you could still use that formula here, it's just your theta would be 90, because they're perpendicular. So in fact this really is, I mean this here comes from this, if you want to think of it that way. So you can just remember this and put the theta as 90 when they're perpendicular, which they usually are, but not always. Okay, got that? Okay. Got that? Yep. Okay. If a force acts on a current in a magnetic field, then could we use this force to do work? So you have your current and you have your magnetic field and they're perpendicular and there will be a force acting on the current. So could we use this force on the current to do some work? Like for example, if instead of a wire that was carrying the current, it was a piece of metal, if the current is going this way and the field is going this way, well actually let's say the field is going that way and the current is going this way, then the force will be going up. So could we use this force to maybe do some work because it's turning? So we can. This is what a DC motor is. Now let me just explain before you draw. So what happens here, you have your positive current coming around here, coming around here, coming around here, and then it goes through this side. Now, the magnetic field is going to the left, so I would have to put my hand to the left, and the current is going forward, so the force is going up, which you can see on the picture here.
It's like
Mm-hmm.
when the current is this.
That's right. And then here, the current is going to U, the magnetic field is going to the right, so the force is going down, so the force is going down here. So because this force is going up and this force is going down, what will happen here? This will start to turn. Now, these aren't pinned together because if you had the wires pinned to this wheel, then when it starts to turn, the wires will wrap up, which you can't have. So the way to get around this, we use these carbon brushes here. So this is not actually physically connected. Fahad, please. This brush is not physically connected to the wheel. The brush is just touching the wheel and they're in contact but they're not stuck together. And notice we have a very important little gap here. If there was no gap here, if this was connected, then the current would just simply go straight through. We must have a gap here to force the current to go all the way around and back out. Okay, so this is a carbon brush and this is called the commuter ring or segment, and there must be a little gap here. This is the armature, which is basically the little thing that moves, that turns. You could imagine a wheel here or something here. These are the magnets, of course. Now, in the exam, they do ask you to draw this. They do. So it's very important that you, as best you can, practice drawing this in your book now, because they do ask you to draw a DC motor in the exam. So this is a DC motor. Yummy. Come on, get off the phone. Get off the phone. Make it beautiful. You drew it, Cara? Show me. Suppose. But have you labelled the parts? Let me see. You labelled all the parts? You need to make sure you have the. Yeah, okay, no problem, okay. Yeah, just write in here carbon brush. It's usually carbon. Yeah. Okay, we got this. Not yet? Okay. Did you draw in the current and the forces as well? No, you didn't draw in the current is going this way. You need to draw, you see little arrows, and then the force, one's going up and the other's going down.
Where's the force going this way?
The red one's the force, yeah.
This one is.
What's this S with
Hmm.
the blue arrow?
Huh? What?
The blue arrow.
The field?
S.
No, what letter?
It was
That's not an S. You know what letter the field is?
it's S, but I can.
No, the blue one.
Yeah.
No. What arrows for field? What letters for field? Think about the formula. The formula you had.
B.
Yes. Okay. Drew this, KJ? You got it labelled with the arrows? Field, force and current. The black one down below. Can you see it? Right here. It'll do. It'll do. Okay, continue now.
Yes.
Yep. So, this wheel is turning. Let's find the torque, or the turning force. So, here is the part which is rotating, and now we imagine that at the end of it, I stick a big wheel. Well, let me try and make that a little bit more pleasing to the eye. So this wheel is turning around. Now, often what you have here is you don't have just one loop. We usually have the current going around many times. So actually, this is in the picture just once, but often what happens is it would go loop around a few times to make more of a force. So in this, we'll say that it's looped n times. So it goes around once, twice, 3 times, n times. Okay. So our formula for torque, turning force, this is an example of a couple. If you remember, you have a force up and a force down. So if you remember, turning force or couple is the diameter multiplied by the force. Now the force we have a formula for, it's BIL, but we must multiply it by n because it loops around n times, so we have more of a force.
Write that down.
Oh yes, yes. Now if this part here is D, and I haven't really been.
What do you call this, this symbol?
Sorry, that tau. That D is actually the same as L because, well, this is L and this is L. It's a square. At least I'm saying it's a square. Although it's not too important that it's not a square. For now, I'm just saying it's a square to make it easier. But if I multiply L by L, what does that make? L squared, which is what? Area. So L by L is the area. So this would be BIAN, or as I like to remember it, I, like in the bank, IBAN. So this is how much turning force you have from your DC motor. It's current times field times area times number of loops. The A is the area here.
Can you go back to the picture for 1 second?
This?
No, the picture, the slide. I
Yeah,
forgot
yeah,
to do
yeah.
one thing.
It just wait, it's stuck right now, I don't know why. Give it a moment. Come on, what's wrong with you? Why are you not working? There we go. What did you forget?
The ARM.
A or armature?
Yeah.
Yeah. It looks more like a square in that picture. Can I continue? Yeah. Right, so actually, you can go back to the slides here. Come on. You can do it. There we go. IBAN, which we have. Right, in fact, just so you know, that that A there, that's the area, of course. But if I would just try my best to draw this here. That's the area there as it rotates around. So in my picture here, it was a square, but in fact it doesn't have to be a square. At least I don't think so. But the formula might change a little bit if it's not a square. In the exam, I think they always use squares. Now, they might not say it's a square, and they should. I think if they don't say it's a square, you are okay to assume it's a square. Okay? So in other words, it really is a square for us. But it doesn't have to be a square, it'll still work if it's not a square. Okay?
This thing?
Yeah, the rectangle that's rotating. Yeah. Okay, remember that flux over some region of space is the number of magnetic field lines over that particular region. Imagine now that the field passes through n identical regions we are interested in. So what we have, I'll try and draw it. Yeah, I'll draw it like this: north and south, and we have our magnetic field going around like this. And we have one region here. So in this picture, what would be the flux here? Well, there's only one line going through this region, so the flux here will be just one. So in this picture here, the flux there will be 1 Weber for this region here. If I stick another region here, which is exactly the same, well, this one has also 1 Weber. So we can call the first one 1 Weber, and the second one is also 1 Weber. So let's imagine I have n of these. Okay, the total flux will be n times the flux in one region, because they're all the same. Remember your formula, so that flux equals BA, or I think actually we said it like this originally, flux over area. So flux density is flux over area, or flux is density by area. So if I just pop that in there, I get NBA. I mean, there's nothing interesting there. It's just saying that if you have the same region and the same situation n times, then we just multiply it by n. But I think there is a special word for when you have total, though. I'll go back to the picture in a sec, don't worry. So total flux is that. Oh yeah, sorry. Yeah. NBA. And I think another word for total flux is the linkage, or the flux linkage. So this is what you need. I'd like you to write this down though. Write and draw. Yep, we drew that. We got this formula. Okay. So now if the field makes an angle theta with the normal of the region of space, then, okay, so here we measure the angle like this. Oops. Okay, so the field is going this way. And if you can imagine, here is our region here, if I draw a rectangle. And then, yes, here, can you picture a little normal on this surface? So this is 90 degrees to the region. So this normal points in the same direction as the field, and the region is perpendicular. Now I know it seems a bit odd. You might feel like, well, why don't we just measure the angle from the plane to the field? But what we usually do is measure this angle perpendicular. So in this particular picture, the angle is 0 because they're parallel. But what you could have is you could have this kind of leaning back a little bit so that it points upwards. So you have an angle theta instead of 0. So I'll draw that a bit bigger. So what we usually have here, here's the field, here's the region of space, and then here is an arrow perpendicular to...
Like a flux,
This is flux, what are you asking me?
it's not surfaces, but
Oh, it can be any shape.
okay.
So in this picture here, can you see that the normal and the field, they are parallel, so the angle here is 0. And then if I was to draw this leaning backwards, so that the normal points upwards, This angle here is theta instead of 0.
With oh yeah, it's the curve.
Hmm.
Yeah, it's a curve.
Okay. So again, we only care about this part, not this part, because we want it to be like this. So here, anyways, is a cos or sine?
Cos.
KJ. It's cos. So if it's at an angle, we just stick in a cos theta here. Finally, the total flux is also called the magnetic flux linkage, mostly. Yeah? Yeah? Yes? Okay. Right, so write this one down. Oh, I should say, that should be 80 degrees. Come on. You can do it. Right, okay, write this one down. No, that should be 80 degrees.
Just 80 degrees is it?
You got this? Yes? Okay. So, let's have a look here. So the first thing, how much current do we have? 2 amps. And what's the length here? 20 centimeters. And the magnetic field density?
3T.
3. What's the T? What's the unit T called? It's not called T. Oh, guys.
Area.
Hello?
Tesla. Come on. So the force equals BIL, which will be 3 to 0.20, which will be 3 times 0.40, which will be 1.2 newtons. Now, if it was at an angle of 80, then the only difference is you have a cos 80, you have a sine 80, (1.18 newtons).
I have a question about the cosine.
Hmm?
I have a question about the cosine.
Yeah, we'll have more questions now. Yeah. Okay, so that's the first one to get us started. Right, the second one, a DC motor is used to turn a wheel. A current of 3 amps runs through the DC motor. The magnet has a flux density of 5 Tesla. The wire runs 1,000 times around the square of length 20. The size of the square is attached to a wheel. What is the torque of the wheel? Write this one down.
What is the water below?
Torque, turning force. Do you remember that?
I have a turning force.
Alright.
Turning field, right? Turning force.
Yeah. let's have a look at it. Okay, so we have our formula: torque equals IBAN. What's the current?
T,
What's the B?
5,
Point T.
5 times,
The area, what shape is it? It's a square, isn't it?
yeah.
So 0.20 squared times 1000. So let's see what we get. (600 Newton meters). Yep. Yep. Okay. Next one. Okay. Got it? Yeah? Let's have a look. So, what you have here, you have an iron rod. and you have a coil wrapped around it, and it's wrapped around 100 times, and you know that this makes a magnetic field. Do you remember what this is called?
Solenoid.
Solenoid. It's 100 times, isn't it?
Yeah.
And it makes a magnetic field. What is the density of the field?
2 Tesla.
2 Tesla. Now, I can't remember, but I think the field goes around this way. I'm not 100% sure. I think so. Anyways, there's a magnetic field going through this here, and we would like to know. Oh yeah, and there's a 5 centimeters here. What is the total flux linkage? Well, that's NBA, which would be M flux, which is NBA, which would be 100 times 2, and the area. Now, what's the area here? What shape is it?
So,
Circle, pi or squared. These are all circles. So that's 100 times 2 times pi, 0.05 squared. Which would be 1.57 Webers. If it is at an angle, then we just need to stick in a cos theta. So for the part B, the cos theta is 10. So for the second part, if I just multiply this answer by cos 10, I'll get 1.55 Webers. Although some books write in n Webers to show that you're counting them up over many different surfaces. I don't feel the need to write that in though. For me it's just Weber. Okay. Got that? Yeah. Okay. Now that should be 70 degrees. Okay. Take a picture if you need to. You got that, KJ?
Check it on YouTube.
Okay. Closing this now. Yes? Okay, I think what I'm going to do now actually